Good. Okay, so we're ready to resume. It's a pleasure to introduce Samuel PÉREZ AYALA. Is that right? Who's going to talk to us about eigenvalue functionals associated with conformally covariant operators.
All right, thanks, Rhoda. Thanks, Asad and Mark, for the invitation. It's great to be here. So let me tell you, in general, what I'm going to talk about, a bit of the setup before going into the specifics. So I'm going to be working on a closed Riemann manifold, meaning compact, no boundary, and n is a dimension. Okay, and I'm going to be considering conformally covariant operators of order k. So my notation is going to be k, g, and here k. So this is a conformally covariant operator of order k. So k is natural number, right? So and then by degree n minus k divided by 2, n plus k divided by 2, which means that if you multiply your metric by positive function, f squared times g, then these operators transform in the following way. So this operator with respect to gf, to this conformal metric, transform as follows. You have f to the minus n plus k divided by 2, and then you have k with respect to the background metric g, and then you have another weight inside here, n minus k divided by 2. So this is acting on a function here, and then you have the function. All right, so yeah, just a comment. I'm not going to be talking about any fractional operators, so hopefully I don't get banned from the conference. But so you should think about the Laplace operator on surfaces, the conformal Laplacian when the dimension is bigger than 3, or the Pennant's operator in dimension 4. Those are going to be the operators actually I'm going to be looking at. Okay. All right. So this is also labeled T. All right. So being in a being in a compact manifold, we have a elliptic operator, so the spectrum is discrete, and the quantities I'm going to be looking at are the following. Okay, you just pick one of these eigenvalues and you define the following quantities. So this is capital lambda bar J. I have the manifold, I have the operator here, and it's going to depend only on the conformal class. It's going to be a conformal invariant quantity, and it's defined as the supremum of, or the space of all conformal metrics. And what I'm going to be looking at is at, say, the jth eigenvalue of this operator, okay, with respect to this conformal metric. But I'm going to multiply by the volume so that we have a scale invariant quantity. This is k over n. And also let me define a similar quantity, but instead of the supremum, I'm going to be looking at the infimum. Okay, so this is put the bar at the bottom. Okay, so this is going to be the infimum or the conformal class of some eigenvalue here of this operator. And again, I'm going to multiply by the volume, then k over n. So I'm being a bit ambiguous here about the way that I'm labeling these eigenvalues, because for some of these operators, the eigenvalues are negative. You might have 0 eigenvalues, positive, right? So what do I mean by the jth eigenvalues? But again, I'm going to be very specific, so this will make sense. But in general, you can always do this, right? You pick one of these operators, and you look at these, look at one particular eigenvalue, and you consider this one. Okay. All right, so Right. So the reason I'm looking at this is because, which is why I'm interested in these quantities, is that as I will explain, and that will be the goal of today's talk. In the case of surfaces, for instance, with the Laplace operator on closed surfaces, metrics assuming D supremum, for each metric assuming D supremum, you have an associated harmonic map into a higher dimensional sphere, right? So these are two seemingly, unrelated problems, right? You have a system of harmonic maps on surfaces. You have these, conformal invariant defined in terms of the spectrum. Two seemingly unrelated topics, they're actually connected. When you look in dimension 4 at the PÉREZ operator, which I will define later, extremals for these quantities are associated with what is known as conformal harmonic maps, which is basically the biharmonic map, but the conformal version of the harmonic map. I'll tell you what that is later on. And if you look at for instance, the conformal Laplacian in any dimension, and you look at the same quantities, extremals for these quantities are going to be associated with either Yamabe metrics, so constant scalar curvature metrics, nodal solutions for Yamabe type equations, and also harmonic maps. So it's a quite rich and diverse theory, and they can all be looked at from this perspective. Okay, so that will be the goal. So let me just write down a few questions that people ask about these quantities. So the first one is, when is it that they are non-trivial? Right, so for instance, for the Laplace operator on surfaces, this is always 0. So the only actually that makes sense is this one. So that is already an interesting question. So you have an operator dimension under which conditions you have non-trivial quantities, and then you can ask the question about whether or not these quantities are attained. Okay, so that's a question about existence of extremizers, right? Maximums or minimums for these functionals. And also, you should ask another interesting question, a very difficult one, is the regularity of those metrics. Because in most cases, you're going to have extremal, but not in the space of conformal metrics, because usually you develop singularities when you try to maximize or minimize this function. So regularity is another question. And the third question, which is what will be my focus today, is suppose that you have one of these special metrics in the conformal class, and it's a nice metric that either maximizes one of these eigenvalues or minimizes one of these eigenvalues. What can we say about this metric? So I'm going to focus on these questions today. All right, continue here. So I'm going to start with the case of surfaces and the Laplace operator there, because a lot is known in that case. And then I'm going to move on to the PÉREZ operator in dimension 4, which is where I have made some contributions. Okay, so let's just focus on the surface case. Surfaces, again, closed surfaces. And the operator I'm going to be looking at is minus the Laplace that will have positive eigenvalues. Okay. So this is an operator of by degree 0, 2, meaning that when you multiply the metric by f squared, this is just from that way. Okay. And the eigenvalue of my convention, usually people, because the first eigenvalue is always 0, usually people denote that eigenvalue by the 0 eigenvalue. I'm just going to denote it by 1. So this is just 0. So the first non-trivial eigenvalue is actually the second one. And it's easier, it's less confusing because I'm going to be talking about various operators for which this might not be true. All right, so this is a fact that I'm not going to prove, but if you look at the infimum and conformal classes, so this is going to be lower bar, right? This is the infimum, this quantity right here, but for the Laplacian in any conformal class, this is always going to be 0 for any eigenvalue. I mean, it's obviously 0 for j equal 1, but for any eigenvalue, it's always 0. So the only interesting quantity in this case is the supreme. Okay. So the first question is it finite? When you maximize in the space of all conformal metrics, is that quantity finite? This one over here. Right, so it took some work, but it is finite. So I'm just going to give you 2 results, although right now there is several proofs. So the first one is forever. This is 93. It proved that these quantities are bounded by a constant that depends on the conformal class, and then you have times j plus 1 here, or just j. In particular, each of these is finite. So he actually proved this in any dimension. So in any dimension, even though the Laplacian is the Laplace operator is not conformally invariant, conformally covariant in higher dimensions, you can still define the same quantities, and he proved these in dimension 2 and actually in any dimension. Dimension 2, you can prove actually something stronger. So let me just mention this result by which is so this is here 2. So they actually for lambda 2. So if you look at the first non-trivial eigenvalue, right? You maximize in conformal classes. This is actually bounded above by 8 pi times the interior part of this number here, alpha plus 3. Gamma plus 3 divided by 2. Here, gamma is the genus of the surface. You actually have a topological open bound, so which means that on surfaces for the Laplace determining operator, you don't have to restrict to conformal classes. You can actually maximize over the space of all remaining metrics, but that's not going to be the topics of today's talk. But that's something that you can definitely do. Any questions so far?
Is there a metric that attains that value?
It's only sharp for the sphere. Yes, so for the sphere, this is actually the value that you get 8 pi. That was proved by, actually, let me just write that down now before moving on. So some examples where this has been computed explicitly. First result in this direction was Hirsch in the 70s. So he proved that the value, that the first non-trivial eigenvalue, conformal eigenvalue, right, meaning this upper bar capital lambda on the sphere minus g, and then you have the conformal class of the round metric, but there is only one, so it doesn't make too much sense. This is actually 8 pi. And there are other known examples. Yeah.
What is the gamma?
The what?
So you have the value is 8 pi and the
8 pi times the interior part of this number, and this is the genus of the surface.
genus.
Yeah. All right, and so you mentioned Lian Yao also proved in 82. This is a paper about conformal area. They proved that on RP2, you actually get the standard. Again, there's only one conformal class, so the value is 12 pi. And in both of these cases, the maximum is obtained by the standard metric, and it's unique, right, of 2 isometers. And there are other examples. So, for instance, there are examples on the torus, where you have different conformal classes, and on the Klein bottle, and also on a specific surface of genus 2. And those are pretty much the only examples. All right. But again, my focus today is to try to explain the connection. So what happens if we have one of these extreme, and what is it that we get? So I want to explain the connection of this extremum to the system of harmonic maps into higher dimensional spheres. So we're going to look at what is known as the normalized eigenvalue functional. So it's the map that takes a conformal metric and sends it to the conformal class. And this is just on surfaces for the Laplace-Beltrami operator. So you get, let's say, J here. I'm just going to write it like this. So this is lambda J. This is the Jth eigenvalue of the Laplace-Beltrami operator with respect to that metric. And you have to normalize by the area. So I'm going to be writing the surfaces as sigma. That. And then the usual notation for this is lambda J GF with a bar. So bar means that it's normalized, okay? Otherwise, so the reason we multiply by the area is that this is scaling variant. Otherwise, all of these quantities are, at least this one is always infinite. So you have to normalize by something, and the more geometrically natural constraint is by, fixing the volume. Okay? All right, so the first problem, so the idea, let me just give you what I'm going to try to do, right? So whenever you have one of these functionals, you want to be able to say, hey, suppose that I develop somehow a first variation formula, and I want to say, hey, critical points for this functional correspond to this particular object, right? So, so that will be the pretty much the method here. We want to take the derivative of this functional and say, hey, derivative, having zero derivative for this functional means that we have harmonic maps into the sphere. The first problem that we find when doing that is that this functional is usually non-differentiable. So by that I mean pick any metric in the conformal class, and suppose that you have a one-parameter family of metrics inside the conformal class, so only consider conformal variations of these metrics, and this map right here that sends T to lambda J of GT. For any J, this is not differentiable, okay? And it's only going to be differentiable when you have simple eigenvalues along the deformation. But that's usually very hard to check, okay? But let me give you a quick example on how to see this on, let's say for a 2x2 matrix. It's very easy to see that these eigenvalue functionals are not going to be differentiable. It's kind of a silly example, but it shows what I want to say. Suppose I have these matrix, 2x2 matrix, and you can check that the eigenvalues are T and then minus T. Okay. So those are the two eigenvalues. And you might say, well, those look differentiable. That is true, but the problem is that when we talk about these eigenvalues, we always order them with respect to magnitude. So when you do that, then lambda 1 of T is actually going to be minus the absolute value of T, and lambda 2 of T is going to be the absolute value of T. So you end up, for the first one, you end up getting the bottom part. So you have a point of non-differentiability when the multiplicity is 2. Okay, so every time you have higher multiplicity, this is not going to be differentiable. Okay, and this is like an easy example of how to see that. Okay, and it's very easy to also construct a sample soon for these type of operators. All right, so how can we work around this? I'm going to explain a simplified version. So this is actually a theorem by, also, it's written in various places, but the way that I'm going to state it is the way that it was stated in this paper. They actually prove that if you have a metric in the conformal class and you have a one-parameter family here that is analytic. Okay. And again, this is just for simplicity. You don't really need analyticity to derive the same notions that I'm about to explain. So what they prove is that it's not differentiable, because again, the problem is about the multiplicity. It's not about how you deform the metric. But at least you can prove that this functional for any j admits one-sided derivative. One-sided derivative at t equals 0. Okay. On both sides. Okay. And that this already tells you or gives you an idea on how to define critical points for these type of functionals. So what you're gonna do is, let me just put definition here. Okay. So we're gonna say that GE. So I'm gonna GE for extremal. Okay. So critical point in the conformal class is gonna be is conformally extremal for some of one of these functional, let's just say lambda j bar, right, the normalized one, if the following happens, if the one-sided derivative have different sign for every possible perturbation. So that's how we're gonna define. So we have the derivative here of this gt from the right and times the one-sided derivative of this functional respect to t from the left. If this has, they have different sign for every possible perturbation of g. So that's the definition. Okay. Any questions? All right. Getting to the good stuff, explain the connection to harmonic maps. So now we have a notion of, you know, what critical points are in this setup, and now I want to say, okay, so suppose that we have a critical point and we prove that we have an associated harmonic map, right? So that would be the goal. So that's the first thing that I want to explain. So the second thing that they prove, so I'm continuing in this self-analysis paper, right? That was the first thing that they proved. The second thing that they proved was that under certain assumptions, so for instance, you have to assume that you might have a cluster of eigenvalues, so you always look at the first one or the last one, but don't want to worry about this too much for today's talk. So under certain assumptions, you can actually, you know that the one-sided derivative exists, but you can actually write them down explicitly. And what you have is the following. So the derivative of this functional from the right is actually equal to minus lambda j of GE. G being some metric in the conformal class that you are deforming. Okay. Times the maximum of this integral here, of this quantity here. So you have h times vi squared dv. So I'll tell you what this is in a moment. Here h is basically the derivative of the deformation. So these are conformal variations. So this is just gt equal to, say, alpha t times g, and h is just the derivative of alpha t 0. Okay. It's just a function, right? You're just taking the derivative of that function. That's what you get here. And phi is just phi here is a orthonormal basis of L2 orthonormal basis of the corresponding eigenspace. So I'm gonna write it like this: EJ GS. G is the metric, again, the metric that I'm deforming. Okay. So this is gonna be the max between, for I in between 1 and whatever the dimension of this eigenspace is. We'll just call it n. Okay. So that's a one-sided derivative from the right, and you have it. I'm not gonna write it down again, but from the left, you get the same, but the minimum instead. All right. So with this at hand, we can prove the following theorem. So let me state that and basically sketch it. We'll tell you what the main ingredients are. I'm not going to prove it because of time, but you want to know the proof is it's not actually that hard once you have these formulas. All right, so again, this is written in various places, but the one that I'm gonna state it is how it's written in another paper by the same people. So this is note 3. And what it says is, so suppose that you have an extremal metric of, so you have GE is conformally extremal for lambda j bar. Okay. Now what you can prove is the following, is that you can find a collection of eigenfunctions. So there is a collection of eigenfunctions. It might not be the whole eigenspace, right? So, but you just have finally many. So these are in the J eigenspace with respect to the conformally extremal metric. Okay. Such that the sum of the squares of this function is identically equal to 1. It's a very strong condition, but that's what you get. And as a consequence of this, you get the following. Well, you have that the sum of the squares is equal to 1, so you can look at this map whose coordinates are these eigenfunctions right here. Well, this is a well-defined map now from your surface into the sphere of dimension p minus 1, right? So we have, at least we have a well-defined map, but you can actually prove that it is a harmonic map. It is harmonic. All right, so let me tell you what the idea for this is. I'm not going to provide too many details, but at least what are the tools improving the first condition. If you have any question, just let me know. All right, so what is the proof of this? So you consider K is going to be a set. It's basically phi squared, where phi is an eigenfunction, okay, with respect to this special metric. Okay. You're going to consider the convex hull of this. So the convex hull is just the intersection of all convex sets containing K. But there is actually a very nice way to write this down. This is just the set of all finite convex combinations. So this is finite, and then you have Phi squared, where Ci's are positive, and the sum is identically 1. Okay. And the claim is, if you think about this, the claim is all you have to show is that function 1 belongs to the convex hull. Well, if you have that, then 1 is equal to one of these elements. You have finally many for which 1 is equal to this, and then the Ci's are positive. You can put it inside that still an eigenfunction. So that will give you this condition. Okay. So how do you prove this? Is by contradiction. You assume that this is not the case, and then you use Hahn-Banach. It's a very classical result, right? So Hahn-Banach separation theorem to separate these two sets, right? This is going to be convex. This is going to be the singleton one. It's just a closed set. So you can find a hyperplane that strictly separates these two sets, and that a hyperplane corresponds to a bounded linear functional. And so you can think of this as living in L2, for instance. That bounded linear functional corresponds to basically integrating against an L2 function state. And then you're going to take that particular function and you're going to show that the perturbation, the one-sided derivative along that particular direction, they have the same sign. And that will contradict the extremality condition. The extremality condition, again, is that for all possible perturbations, these always have different signs, but you can prove that that along these particular perturbation, after applying again, and connect, and previous result, so previous result. By this I mean the formulas for the one-sided derivative. You can prove that you can find a direction along which the one-sided derivative have the same sign. So that contradicts the external condition. So that will be for the first part. And so this is for say 1, and then for 2, just differentiate the constraint. Apply the Laplace operator to that, and what you get, so you can do this, right? Apply the Laplace operator to this, expand, and what you get is that lambda j of g epsilon is actually the differential, the normal square of this, of the differential of this map. Right? So as a final comment, so let me just move this up so that everyone can see it. Remember what we have. So these are eigenfunctions with respect to the same eigenvalue. So what we have is that minus GE of phi I, so phi i's are the components of this particular map that I defined there, is going to be equal to this normal square of the differential times phi I. Okay, if you have seen this type of equation before, this is the harmonic map equation for maps into the sphere. Okay, in general, it's a bit more complicated to define, but when you have, I guess this corresponds to the extrinsic version of that. And when the target manifold is a sphere, this is the equation that you get. So again, the key point is proving this, and then this is just an easy consequence just by differentiating on the constraint that you have. All right, so that's a connection to harmonic maps, and you can actually go back. So I'm not going to prove that, so I'm just going to mention what the result is. So again, this has been written in various places. So the way that I'm going to state it is in a paper by Mikhail Karpugin and Mekles. So this is actually quite recent. But this connection was first observed by Narilashvili when he was working on the same problem on the torus. He was the first one who that observed this connection. This is 96. So the statement is quite stated is quite simple, but suppose that you start with a harmonic map from the surface into the sphere. So non-degenerate harmonic map. Non-degenerate means that the differential doesn't vanish. Okay. Then the conclusion is the following. Then there is a conformal metric, right? Such that G, this particular metric is conformally extremal for some lambda j. So for one of these eigenvalues, and the j that you get here is actually called the spectral index of this particular map, if you know what that is. Okay. All right. So now I want to mention in the last 10 minutes, I want to mention what is known for dependency operator in dimension 4. And if you have any questions, let me know. For manifolds, so now I'm going to move to 4 manifolds. And I'm going to be looking at I'm just going to denote it by PG, right? So this is the dependent operator. So the main part is the bi-Laplacian, and then you have some lower ordered curvature terms. This is of order 4. And based on what we know about the Laplacian of surfaces, it makes sense to look at these quantities, right? So the supremum and conformal classes. So let me just write it this way. So we're going to be looking at the supremum. So what can we say? When is it finite? So upper bounds. That's the first aspect that I want to discuss. So this is something that I did recently. The first thing that you can prove is that any of these eigenvalues, so these are called the conformal eigenvalues, these supreme and conformal classes. This is actually finite. So you have, the way that I wrote it is some constant that depends on the conformal class. Now this is not shard. We don't have any information about what this constant is, but at least they're finite. So it makes sense at least to propose a question about whether or not we can find a maximizer for this, for these invariants, right? Something that attains this supremum. So that's the first aspect that I wanted to mention. So now let me try to explain what is the connection of this. What is it that we get if we have an extremum for the same normalized eigenvalue function? Well, not the same one, but the analog of what we considered before. So we're going to be looking now at this functional, conformal class, conformal metric, and we're going to map it to the jth eigenvalue of this operator. Okay. And you have to normalize by the volume. There are other normalizations, but this is the most natural one. Okay. And remember, when I wrote these quantities here, you had k over n, but the dependence operator is order 4. We are on dimension 4, so you only see 1 there. So this is the function that I want to consider. I'm going to use the same notation. So this is going to be lambda j gf bar, but now these are the normalized eigenvalue for the dependence operator. Okay. So what is it that we can say? So we have the same issue. Obviously, this is non-differentiable. So we have to develop what the notion of having critical points is in this setup. And so this is another result that I wanted to mention. We basically get the same results. So I'm just going to write here same results, meaning that pick a metric in the conformal class, deform it inside the conformal class analytically, then you have the system of the one-sided derivative. Okay. Again, this analyticity condition, it can be dropped. So for instance, if you know this paper by Fraser and Shen, where they were studying the eigenvalues for the Dirichlet to Neumann map, and they were trying to basically maximize those eigenvalues, and they noticed a connection from that to free boundary minimal surfaces in the unit bulb. Another thing that they proved there is that you can actually drop that condition from analyticity to just smoothness, right? So you don't need analytic metrics or anything like that. So the same can be applied here, but again, for simplicity, I'm just going to stick to this. But anyway, same results again. I mean, you pick an analytic perturbation in the conformal class, the one-sided derivative exists, and that allows you to define what critical points are. So there is a notion of critical points, okay, in the same way that we defined it previously. And the formulas are pretty much the same. You can actually find formulas like that for the dependence operator. So that's also part of the result there. All right, so let me just write down what we get in this case. I'm not going to prove it in this case, but at least I want to mention what we get. All right, so what are the critical points? Critical points correspond to what, right? So again, in the surface case, you have harmonic maps here. So let's see what we get in this case. So this is, again, something that I did, same paper. So suppose that you have one of these conformally extremal metrics. So you have a critical point of this functional, the conformal class, okay? And for, let's say, for the normalized lambda j function, okay? So the result is, it looks the same, right? So what you get is that there exists a collection of eigenfunctions. Now these are eigenfunctions for the PÉREZ operator, obviously. So these are the jth eigenspace back to this metric, such that the sum of the squares is equal to 1 on the manifold. Okay. So we again have a well-defined map into the sphere. So here, the coordinates are given by these functions that we found in part 1. Okay. So this is well defined, but it's not going to be a harmonic map, at least not in general. It's going to be a what I call a PÉREZ map. That's a bad name, but I couldn't think of anything else. I think in some people call it conformal harmonic maps. For instance, this is in a paper by Gerard, I think in 2008. He was working with kind of like the intrinsic version of this, but the way that I like to think about this is the extrinsic version of this. So I'm going to write it down what it means specifically. So again, what we have is, again, it's the same idea, right? So you have this constraint, you derive it in the same, pretty much in the same way, and now you want to differentiate this constraint, but what you get here is that this map now satisfies the following equation. So I'm just trying to explain what I mean by this word right here. So now you have something that I'm going to write like each. So this is the epsilon. I'm sorry, GE. Times this. What I mean by this is coordinate wise. So you apply the PÉREZ operator to any of the coordinates of this map, and then you have something times that. Okay. So this is basically the eigenvalue with respect to this extremal metric. So just compare with what we have in the Laplace case. In the Laplacian case in surfaces, you have the operator acting on this map, and here you have this, what is called the density. Or I guess I'm missing a constant there, but the norm square of the differential times this. This is a harmonic map equation again on surfaces for maps into the sphere, and we get the similar structural list here. But the formula for this is a bit messier. I'm not going to write it down, but it's basically what you see in the energy of the PÉREZ energy. Okay. All right, so this is what I mean by PÉREZ map. We have a map that somehow satisfies this equation with this particular quantity here. Okay. And conversely, this will be final point here. On the other hand, if we start with one of these maps, so if we start with one of these maps from your manifold to the sphere, okay? Yeah. Oh, yeah, Okay, so let me just say that if you start with a map into the sphere, that is a PÉREZ map, then you can go back and so there is a conformal metric that that is extremal for 1 lambda j. Okay, it's the same result, but for the PÉREZ map. So that's all I wanted to do actually. So I was going to finish there. Yeah. Sorry about that.
So, questions?
You do the one-on-one information of P, the dimension of this place.
No, we don't.
So how does that help? After this result, how does it help?
Right. So in dimension 2, this actually tells you what the best possible regularity for maximizer of these functionals are. So the regularity in dimension 2, so actually you can write explicitly so in dimension 2, there are existence results already, and the maximal function, so G maximal, is actually of the form, this form. Where these, if you think about the classical, regularity result for harmonic maps, at least when the domain is a surface, these could vanish, but only at finitely many points. So the best regularity that you can expect, at least on surfaces for Laplace operators, is understood in terms of the regularity for harmonic maps, and this actually tells you also what is the right space to maximize these eigenvalues. It might not be the conformal class, so you have to weaker that notion. So the analog of this will be, hey, if you want to understand the system problem, but in particular the regularity and what is the right space to kind of try to maximize these eigenvalues, we have to understand what the regularity for these PÉREZ map are. I don't think that has been done. It has been done in particular cases. There is some results. But I think in general, what we need to understand here is what is the vanish, how large can the vanishing set of these could be. That will tell you what the regularity for these maximal metrics are for the PÉREZ operator, and also what is the right space to do the maximization procedure. So it's about the regularity. Understanding this connection also tells you what the regularity is and what the right space should be to start the maximization process.
So this energy is just a P. Phi
Pretty much.
I.
You have some other lower terms, but it's really hard even to get a sign on this, right? So, but yeah, understanding the zero set of that will be, a natural next question, but doesn't seem to.
What happened to lambda j minus the lower bound? The lower bound.
The lower bound. I think in some cases that's going to be 0. So suppose that you have you assume that the PÉREZ operator is non-negative with trivial kernel, right? Constants. I think we can also prove that the lower bar is also 0. The same as it happened for the Laplace on surfaces. So this will be like the only interesting question. But it's not like that for general operators. So for instance, for the conformal Laplacian, if you look at the first one, so assume that you have a positive Yamaha invariant, and you look at the first eigenvalue, and you try to minimize in conformal classes, what you get is actually the Yamaha invariant. And the extremal comes in the same way. And an extremal for the first eigenvalue functional is a Yamaha metric. And if you start with a Yamaha metric, it's an extremal for that eigenvalue functional. So the minimum is not, the infimum is not in general 0, but it's 0 for certain operators.
I mean, I guess what I was going to have a question which is linked to what we were just talking about then. So you're looking here at the Laplacian in dimension 2 and then PÉREZ in dimension 4. But if you look at PÉREZ in other dimensions, then you wouldn't be acting on just functions. In a sense, you'd be acting on densities. But
right,
so you get similar results. So.
Right. So there is again, we have to be careful when it's subcritic, like when the order is less than the dimension, perhaps. So in general, there is a result by Aman and Hammonds, I believe, that this. So if you look at the first positive operator, positive eigenvalue for one of these operator, and the order of the operator is less than the dimension, then that supremum is always infinity. For instance, if you look at the eigenvalues for the conformal Laplacian on the sphere, the order is less than the dimension of the manifold. The supremum is always infinity. Right, so we have to be careful how to do it, but we could maximize, for instance, negative eigenvalues. That's something that, for instance, Matt and I did 2 years ago.
So no further questions? We'll thank Sam again. We've got a short break until 12:30.
So a small remark for those of you who went to the canteen yesterday and who want to receive, please write us an email. Maria and me, you can find the email address on the website of the conferences, and write us an email, and we will try to make something that looks like a receipt, confirming that you paid the price of the canteen. Okay.
Thank you.